there we have it. Okay. Nuts. I guess it's Zoom. It's slow. And so then I hit it again and then it goes on. Okay. So I want to show several different applications. Hoping that will help people get a feel for how they could use these, how they might use these tools. And the first, sorry, I'm gonna close something. And first application is something we've just been, Bashak and I have just been doing in the last couple of weeks. And there's still work to be done on it, but it illustrates, I think, one use of this. So Bashak is doing, has long since actually finished, these experiments on very long interval timing in mice responding to a CS, the design is explained here in this slide. There's milk reward. The response is poking into the hopper where the milk is going to appear. It's a chain lever pressing protocol. So the mouse presses one lever. Oh, so it's not poking, it's pressing. I just do the data analysis. So, for me, they're just responses. So it's lever presses. And the mouse presses one lever in order to gain access to a second lever, which then pays off with a reward. The way it works is that the mouse makes, after it's received a reward, it goes back to the lever, the first lever, makes one press, which turns on the lights, the house lights, and it starts a fixed interval, which can last up to 2 hours. So you can imagine a mouse pressing a lever. You're going to see records of a mouse pressing a lever for 2 hours in order to eventually get a reward. Now, when it does finally get the reward, it gets a big reward. So it isn't starving to death. It isn't working itself to death. She first trained them on a VI and then switched to the FI and started at 20 seconds and increased them to 60 seconds and then finally to an hour. And then a subgroup was eventually extended to 2 hours. So the data that we're going to be looking at are response rasters, right? If I can get and here they are. So this is the cumulative response. Can people see my cursor? I hope I'm on the left panel here.
Yes, we can see it running.
Okay, good. So this is the cumulative record of the animals responding during a 60-minute FI. And as you can see, it starts out at one low rate, and then there's an abrupt change to a higher rate. And what we want to do is identify where those changes occur. And to do that, we estimate the initial rate from I think she used the first 15 responses. So that one might take you up to here because the initial rate is very low. So that's our estimate of the initial rate. And then we use the Kullback-Leibler divergence to ask at what point does the rate diverge from that initial rate, all right? And we're plotting the Kullback-Leibler divergence here in red. And the asterisks are where it passes through various criteria for whether there's a significant difference. And as you can see, one of the nice things about this is particularly when you have this kind of clear separation, the Kullback-Leibler rises so rapidly that it doesn't matter basically what criterion you want. So this is a criterion for 0.05. And this is 0.01, and this is 0.001. But as you can see, regardless of what criterion you choose, the estimate's going to be the same within a very few presses. And you'll see that, and oh, by the way, down here is the raster plot. Let me get this out of the way. So here's the raster plot for this. So we have here the raster, here's the cumulative record, and here's the MDKL. And as you can see, and these are the last 5 1-hour sessions, 1 run per session. And so you see that just by glancing at the rasters, you can see that there was large variability in when the animal began to respond more rapidly. So here he began after a little less than 30 minutes into the hour. Whereas here, you see a slower progression through the thing. So he began, this is this raster down here. And here's where he went through the very low criteria, and here's where he went through the next more stringent criteria. This is the 0.05 at this point. Here's the 0.01, and here's the 0.001. So they only satisfied the really stringent criteria. Very near the end, right? But it is capturing the fact that even on that run, the subject did increase. So you see, in general, you get this very abrupt. It's not always that good. One of the things you see, actually, I think it'll be more apparent in the next. Okay, come on. Oh, there we go. Okay, here's another subject. Now, I chose this partly because this subject was responding much more rapidly. This is the raster plot, right? Just to show that it works pretty much no matter how they're responding. And again, what you see is this extremely abrupt rise of the evidence. What we're plotting here is the strength of the evidence that the animal has begun to respond more rapidly. Right? And of course, it's very easy to do. Bashak did not do this in real time, but it's perfectly possible to make this plot as the data come off the out of the box. All right. You can set up an automated system where it's downloading the data as they're generated and analyze these things in real time, which for me, the way we used to do it, we'd run an experiment and then we wouldn't analyze the data for an hour, for months, sometimes years. So we wouldn't really know what we had until we got around to analyzing the data. And of course, it was a fairly frequent experience that once you analyze the data, you said, oh, shit, look what they're doing. We should have run such and such a condition, right? So part of what I like about these new tools is they really invite doing the analyses in real time. Okay, so that's determining where the run, the rapid responding begins on a fixed interval schedule. So the next example comes from work done by Peter Balsam over a number of years. Peter and I have been working on we still haven't published this, and I think the experiments were finished 5 or 6 years ago. Anyway, when we do publish it, it's going to be great. We've sent it to Science and Nature, and of course they turn it down as they always do. So we're revising it for other venues. So in this experiment, there's milk reward at random intervals. The average interval between the delivery of a milk, this is Pavlovian conditioning. So the milk is delivered completely independent of whatever the rat does or does not do. But it's delivered only during the intertrial intervals, only when the tone CS is not present, okay? And those intertrial intervals are exponentially distributed. The tones, on the other hand, have a fixed duration. So in any given group, it would come on for 10 seconds or 20 seconds or 40 or 80 or even 160 in one group. So this is looking at the effect of the C to D ratio in inhibitory conditioning, which, to spill the beans, is basically identical to its effect in excitatory conditioning. And that's so the question is, how many reinforcements, USs, did it take for each rat to acquire? As usual, we're doing this rat by rat, not group averages. There should be a general ban on group averages and work on associative learning and timing. And acquire in this case means, when do they begin to poke more rapidly during the ITIs than they do during the CSs? So I want to stress how simple the data are. That's why I'm showing this. This is not rocket science. This is really simple, right? You have the cumulative number of responses in this column that the animal has made. Little r stands for response, big R stands for reinforcement. So in this column, you have the cumulative number of responses that the animal has made during the CS. I remind you that it never gets a reward during the CS. And you have the cumulative duration of the CS, which you see here is increasing in 10-second increments, because for this animal that I'm about to show you, the CS was only 10 seconds long. And so you divide the number of responses by the time, and you add 0.5. That's where the Bayesian comes in, right? That's how fancy Bayesian analysis is. All you do is add 0.5 to the n. And so you divide the number of responses made during the CS plus 0.5 divided by the cumulative duration of the CS. That's your Bayesian estimate of the rate of responding during the CS, which is in this column. And similarly, you do exactly the same thing for the ITI, right? So how many responses has the animal made during the ITI? What's the cumulative duration of the ITI? This is in seconds. And then you add 0.5, divide by the duration, you get the rate. And then you plug those two rate estimates into the NDKL function, for the exponential, right? So that in this column, you have the strength of the evidence that the two rates that you've calculated differ, which is the thing that you're interested in. And Peter Latham, bless him, proved that this statistic is distributed gamma 0.51 regardless of the n. So it's a very simple statistic. And so it translates, because it has a known distribution, these values translate into p-values. I actually think that the NDKL is a better measure of the strength of the evidence. It's a physically meaningful measure, for one thing, because it describes the amount of memory that can be saved by recoding the data from the two different periods, taking into account the fact that they actually come from different distributions. Okay, let's see if I can get this to advance. Right. Okay, so here's a somewhat complicated plot, but you grow to love them. Here in the black, the heavy black line, is the estimate of the poke rate during the ITI intervals, the intervals between the CSs, right? And the dashed line is the estimated poke rate during the CSs. So that you see that this particular subject, and there were quite a few subjects like this, actually started out poking more rapidly during the CS. Remember, it's never going to get rewarded during the CS. But it started out poking very significantly more rapidly. That is, the red here is up to 20. So the evidence that this difference is real is astronomical. Keep in mind the p-value is 0.001 when we get here to the level of 5. Now, of course, that's not what we're looking for. We're looking for when does it begin responding more rapidly during the ITI. We pretty much know, at least when the eye up here is favorable, that that will eventually happen. And this point here is where the rate estimates cross. Right? But you can see that they're hardly different at all. This value for informativeness is very marginal. Unless you run thousands of trials, a non-trivial fraction of the rats in the group will not acquire with this. I'll be saying much more about informativeness next lecture, but it's for those of you who know what the C to T ratio is, it's the C to T ratio. So you see that with this very poor C to T ratio, that basically the rates don't differ. This is the point at which the dashed line became permanently less than the solid line. And while that's true, it's also true that it's only barely less. And the NDKL is telling you that, right? The ND, this line here is for the 0.05 level. And the NDKL is bouncing around down here at chance, right? Telling you that the evidence for this difference is very weak. Okay? But at this point, you look and you say, oh, look at that. Finally, they diverge. And sure enough, then the NDKL goes down. When it crosses here, it's beyond the 0.01. Now, how do we get a negative NDKL, right? The NDKL, I remind you, the DKL is always positive. All right, important not to forget that. However, when the thing you're interested in the evidence for can diverge in either direction, it's very confusing to have the NDKL. So if I didn't do what I'm about to explain, the NDKL at this point would start back up again, right? And when you'd look at it, you wouldn't realize that what was going on back here was very different from what was going on here. So in the function that computes this, you have the option. You don't have to do this, but you have the option of choosing to add the sign of this difference to the, that is, you endow the NDKL with the sign of this difference. And so now the NDKL goes down. This is inhibition, right? We sort of think down, that's inhibition. So you may notice that the response rate during the ITI actually hasn't gone down at all, or only very little. And in fact, spilling the beans a bit, that's a general finding. What actually happens in quote inhibitory conditioning is not that the average response rate during the CS goes down, it's rather that the response rate during the ITI goes up. And you'll see, I think, the same thing. Yeah, so here's now another subject with a considerably more favorable informativeness, right? 5-to-1 ratio of the context rate of reward to the rate during the ITI. I'm sorry, the other way around. 5-to-1 ratio of the rate of reward during the ITI to the contextual rate of reward. Keep in mind, these are Pavlovian experiments. When the animal's put in that box, it gets these rewards, even if it goes to sleep. Okay, so these behavioral effects are based purely on what it observes. So you see that this animal acquires very much more rapidly, right? In fact, it acquires so rapidly that in a moment I'm going to change the X limit so that we can see what's really going on down here. And you see that it acquires decisively, right? I mean, it goes along at chance and then boom, just as with the mice in the fixed interval, it blows through these different significance levels very rapidly. This is the 0.001, you know, it's 1,000 to 1 odds against there being no difference. So in almost anybody's book, that is decisive evidence. So now in the next, this is the same data, but I've zoomed in. I've changed the X limits and the Y limits so that we can see in more detail what was going on during the period when the animal actually acquired the conditioned response. And you see that this mouse, the rat, sorry, this rat started out pressing, unlike the previous rat, this rat started out pressing more rapidly during the, or poking, I should say, during the ITI than it did during the CS. And that never changed. It was always less. But it wasn't significantly less. You see here the NDKL, which is being plotted against this axis, is bound. The chance range is in here, and it's bouncing around until we get to this point at which, boom, you can see the difference became bigger, and this was permanently bigger. Our criterion is that the DKL, the NDKL, not only cross these lines, but that it never returned. In these experiments, it's very, particularly when you get to the P.001, basically they never returned. There were like 60 rats and maybe one or two of them returned. But we always count it when, we only count it when they stay, when the evidence stays above a given level. So let me stop at this point. I'm got another couple, or at least one slide to show to see whether there are questions.
Randy, I might have a very quick question. In the first data set that you have shown, the NDKL index actually goes above the criterion that you have set very fast.
Yes.
But in your coverage of where the change point was, it seems like those evidence were ignored. So do you have a rule of thumb that allows us to do that?
I do. As you might imagine, Peter and I played around a lot with what you appropriately describe as a rule of thumb. And there isn't a one-size-all-fits-all rule of thumb. So returning, for example, to the, let's see if I can get back there. Yeah. So if you look at this, you see, these are the kind of data you're referring to, right?
Exactly, especially the second session. There is a more clear case of that.
Yeah, you see, for example, that there isn't that. In fact, this animal very clearly has two transition points, right? At least two. So there's one right here, which is picked up, and then there's a second one. And here you see, right? He had sort of what you might call a false start, whatever. Anyway, he started off running and then he slowed down. Keep in mind, he's doing this for 2 hours, so probably stopped the groom, but then takes off again. And here again, look, you see, right, that there's an acquisition point here, which isn't obvious in the record, but which this tells you is actually the evidence for is very strong. Then it looks like there's another change here and another change here and so on. We haven't worked out the rules of thumb for this yet, but one of the things I'm quite sure we will do, which we've done in other situations like extinction also, is run the algorithm both ways. So you limit you can specify an interval over which the thing is, the rate is increasing, right? So if you start at this end of the data, and run it backwards, right, then you're going to
Exactly.
find a change right there, right? And then you can say, okay, this animal was accelerating between this point and this point, which that that's, I think, pretty good description of what was going on. So you have to combine the measure of the strength of the evidence with, you want to capture what you can plainly see, and so um, you do this until you're happy. Returning to those data with Peter Balsam and I, we sat and we worked with several different rules of thumb, and we weren't happy with most of them, but we eventually found one that we were happy with. What does happy mean? Well, when we looked at the cumulative records, we said, that's the point we required. And we had an algorithm that agreed with us basically 100% of the time. So that's what we were happy about. Hang on. So we sat there for 2 hours and we looked at, there were 60 subjects, right? We looked at the curve for every single subject and we both agreed. We said, yep, that that nails it, right? So that's the kind of thing that you do. But the nice thing about more or less automatically getting a number of different significance levels is that you can and you should say, well, look, one could argue about when the evidence is really strong, right? So we look at the cumulative distributions of acquisition points, for example, as a function of the strength of the acquisition criterion, right? And again, what you see is that this doesn't affect your conclusions at all. I mean, of course, as you strengthen your criterion, the acquisition point moves towards somewhat longer trials, but the effect of informativeness, for example, is completely obvious, regardless of what acquisition criterion you use. And of course, that at the end of the day, that's what we're interested in.
So your response to the first data set and to a certain extent to the second data set is very theoretically convolved. That is, there is a single acquisition point, right? So
there's a point over which he's acquiring, right?
That's right. So, but
ends you get. So this would be relevant to Justin Harris, for example. Justin Harris has been arguing with me, and he's right. Actually, we published, as you know, back in the day, paper saying that acquisition was abrupt, and yeah, well, it often is abrupt, but it's not always abrupt, particularly when the informativeness is low. And so then the question is, how do you characterize the interval over which it's accelerating? And I just described to you, right?
No, that's right. So I just wanted to bring this up because for most of the audience out there, there is not necessarily a theoretical guide or a prediction. That it might be all theory free, and they might be interested in finding multiple change points if there is in data set. So that's so running the algorithm backwards and forward might be one way to detect at least two if there are two.
Yes, exactly. I've played around with using it recursively, where every time you find a change point, you say, okay, we'll cut the data at this change point and then we'll start over. So far, that doesn't work as well as my old algorithm, that change algorithm that's now 20 years old, right? The CP Raster algorithm, right? Which has been very widely used by a lot of people. So when you really want to find multiple change points, as of the current moment, at least, CP wrapper is better for multiple, particularly when they go up and then they go down and then they go up and then they go down and so on. Now, maybe by a little more fiddling and understanding the situation a little more deeply, I can make this NDKL work recursively, but so far my efforts to do that haven't borne fruit.
Thank you, Randy.
Okay, now, another collaborator, Tim Sheehan at Utah State. So this is, how long can you postpone the reward in an operant conditioning protocol and still get the animal to learn? And as most and many of you know, the gospel has generally been, well, the reward had to come very quickly. And in most reinforcement learning models, even contemporary ones, they routinely assume that the reinforcement comes in the same state in which the animal was in when it made the response. But when you put a 2-minute delay between the response, the rat, and you just watch what happens. Of course, the rat does a lot of other stuff. He makes a response and then he grooms, he makes another response. He might make 20 responses, all of which in this protocol have no effect, right? In this protocol, once you've made a response, you're going to get your reward in 2 minutes, but anything you do in between won't have any effect. So they were trained, they were hopper trained, the usual sort of drill, so that they were used to eating out of the food hopper. And then they had an hour of context extinction. This is very important. This was essential to reduce their, basically to bore them so that they weren't running around and doing much. And then they were placed back in the box that they'd been hopper trained in, but now there was a lever in that box. And rats, being the curious creatures that they are, they noticed that lever sooner or later. And they gave it a press, and often several presses, particularly initially. Now, these were yoke controls. So there were paired rats, and one rat was actually triggering they were in 2 different boxes, but one rat was actually triggering the reinforcements that were being released in its box. So its behavior was triggering it. The other rat, its behavior in another box, its behavior was completely, it didn't do anything. It just got whatever reinforcements the first rat received at exactly the same time as the first rat. So everybody clear about this yoke control design? Okay. Now we have to, and you'll hear more about this in the next lecture, but when we come to operant conditioning, we have to distinguish between prospective association and retrospective association. So we're measuring association, and again, I'll be explaining this by essentially the mutual information, which I've already explained what mutual information is in a previous lecture. In the next lecture, I'll show how you can use that to measure the strength of an association. But it's very important to realize that now we're not talking about anything going on in the brain. We're talking about an objective fact out there in the world. That is, when, quote, you measure the association using this procedure, this information theoretic procedure, you're measuring an objective fact about the animal's experience. So the prospective association is the amount of information that a response provides about when to expect the next reinforcement. Right? So you saw, for example, in the FI thing, that Bashak's subjects, some of them made thousands of responses during the FI without getting a reinforcement, right? Think how that works in a story where they update, they depotentiate the synapse every time they don't get reinforced. So obviously in that situation, most of the responses provide no information whatsoever about when you're going to get the next reward. To know that, you have to be timing. And of course, we know that these rats are timing. They've started this interval and they've learned that this interval lasts 1 hour, and they're not quite sure when the hour is up, so they start responding well before it is up. In variable interval schedules, when you compute the information, once the animal's begun to respond rapidly, they respond much more rapidly than they're getting reinforced. And so if you ask how much information does a response provide about when to expect the next reinforcement, it's unmeasurably small. Right? But there the animals, oops, there the animals are banging away. So what's going on? Well, people have had an intuition forever, going back at least to Skinner, actually back before that to Tim. Who am I thinking of? Anyway, I'm blocking on the name of a famous earlier reinforcement. Back, I'm talking 1920s. The people have had this intuition that in operant or reinforcement learning, the reinforcer works backward in time. And people, that's always bugged people, right? How could that be, right? Why are they bugged by that? Because they don't believe the animals have a memory. But of course, if they remember what they've done, then there's no mystery about how it can, how a reinforcement can work backwards in time. And you capture that really nicely in information theory by asking how much, suppose I tell you that there was a reinforcement here. How much does that reduce your uncertainty about the recency of the most recent response? Right? If you look back through the record, does the recency of the most recent response look like what you would expect just because the animal is banging away at a certain rate? Or does it look much shorter than those intervals? Why? Because one of those responses finally triggered a reward. So the important point is that the retrospective and the prospective associations can be extremely different. One of them can be zero and the other can be very strong, or we'll see here that in some data that came from Cheyenne's lab, both of them were very strong early on. So in both cases, the measure of the association is the mutual information, which is, here's for the retrospective case. So let me walk you through this notation here, right? Capital R, that's the reinforcement. The arrow above it says we're looking back from that, right? So we're estimating the rate of responding by looking backward from the reinforcements. And we only look back to the most recent response, right? We don't look, so, right? So conceptually, this is really an average interval, right? But for deep mathematical reasons, throughout all of this, we convert our average intervals to rates. And so this is just the reciprocal of the average interval looking back from the reinforcement. And you compare that rate to the average interval between responses. Right? So this is your marginal distribution, the rate for your marginal, and this is the conditional rate. For the prospective, you're looking forward, right? You're looking forward from responses with an arrow forward to what is the rate of reward when you look forward from the response. What you do here is you find every response and you measure the interval from that response to the next reward, regardless of how many responses intervene. Right? So that's what gives you this rate. And now you begin to see why this measure can be very different from this measure. Wow. Okay, so one of the things I've stressed is what I really love about these way of proceeding is that you apply the same data analytic techniques both to the stimulus, the thing you manipulated, the animal's experience that's driving the change in behavior, and to the change in the behavior itself. And in these two plots, what we're looking at is the strength of the prospective association and the retrospective association over the first 10 rewards for, remember, these are yoked subjects. So the solid line is for the subject whose behavior is actually producing the reward. And the dashed line is for the subject whose behavior has nothing to do with the reward, but he's getting whatever rewards are produced by this. So there is no association here. There may be a fortuitous association, as you see right here, just from small sample error. But in the long run, because there is no contingency between this subject's behavior and the rewards, it's very close to zero. And in fact, he ran this for hundreds of rewards, and you can trust me that the dashed line here was right. And the association, the mutual information between this subject's responses and how soon it got reward was negligible. Whereas this subject, the mutual information was up to 8 bits. And we're going to see next at the next lecture that 8 bits looks like kind of a magic figure. But it was up to 8 bits by the third reward, right? And it stayed up there. So there was a lot of prospective information. And over here we have the measure of it. So this is how strong the association is. And this is the measure, the NDKL, of how much we should believe that it's this strong, basically. It's the strength of the evidence here, right? And we see that, remember, 6, by the time you get to 6, you're beyond 0.001. So this is at 6 by, after the first, well, after, I forget exactly how I tallied these, but after the second or third reward for this subject, right, the prospective, and whereas the evidence for the others, for the yoked subject, is very weak. And now here's the retrospective contingency, mutual information, right, for the same 2 subjects. Now, how do we get negative mutual information? If you remember the basics of mutual information cannot be negative. But to compute this, we're doing the log of 2 empirically estimated ratios. And the constraints are that as on how we choose those ratios, the constraint, whoa, sorry. It just, the trouble is if you start messing around with the, how do I start over? I'm sorry. Where's the icon that I have to click on? Oh, here it is. Hang on. Okay, bring back our. So here's the retrospective contingency, which you see is mutual information, delta H, the change in the information, how much less uncertainty you have about how recently a response occurred once you know when the reward occurred. This is for the subject whose behavior actually is triggering the rewards. This is the strength of the evidence, and this is negative DKL. Now, the negative association and the negative DKL here are not because of the business of assigning sign that I described earlier. These are due simply to small sample error, right? The entropy of the conditional distribution will always be essentially 0 if there's no contingency. I'm sorry, that's exactly wrong. It will be. The entropy of the conditional distribution will be equal to the entropy of the unconditional distribution when there's no contingency. And asymptotically, that was true for every one of these subjects. But through small sample fluctuations, that isn't necessarily true when there's very little data. And that's what gave rise to the negative associations here. And similarly, that's what gave rise to the negative DKL. I think maybe I did assign sign there. Anyway, that's it. I hope that gives you a feel for the diverse ways in which you can use these tools. And I think the most important take-home message is that these tools lend themselves extremely well to analyzing your data datum by datum. And when you're interested in changes in behavior, that's a cool thing to be doing. And another big advantage is the way in which you sort of automatically get effects at many different significance levels. In the old way of doing things, you would choose a criterion. So for example, trials to acquisition in pigeon auto shipping, which will be a big focus next lecture. Those data now are 40 years old. And back in that day, they took advantage of the fact that the pigeons very seldom peck the key if it doesn't predict reward. And so you have essentially a zero rate before they begin to perceive the reward. And then they adopted a criterion of the bird had acquired when it made at least one peck on at least 5 successive trials. Which is fine. I mean, the data that emerged from that are beautiful. So, I mean, it's not really a problem. But when you do that, you're always saying, well, what if it was 4 successive trials? Or what if it was 4 out of 5 trials? And so on. That is, the criterion is essentially arbitrary. And it always sort of lingers whether that might have affected your conclusions. And when you use this method, I wouldn't say it guarantees you're not going to have that problem, but you always continue until the NDKL has become astronomical. So there's never any doubt that there was an effect. And then, as Fu had said, okay, one can then argue about where the effect appeared, and one will argue about it. But in those earlier slides, I didn't call attention to this, but yeah, I deliberately used a number of different criteria, including very weak criteria. So in returning to what Balsam and I were deciding, when did these animals actually begin to respond? And so one criterion, which was sort of the extreme lower end of what you could possibly argue, was that they began to respond after the first trial in which their rate was higher during the ITI than during the CS, in which case this animal began after the first trial. Now, very few people, even including us, are going to buy that as any sort of, you can't get an error estimate on it for one thing. But now this line is for when the odds, after this line, the odds are 2 to 1. That's a P of 0.33. So you wouldn't in general get that into any journal, right? But if you're interested in the fact that you're dealing with a phenomenon in which the evidence is growing stronger over time, that's the nature of the phenomenon. So if you want to understand the interval over which it's growing, you should start with weak criteria. And then this criterion is 10 to 1. And this criterion is 20 to 1. And this criterion is 100 to 1. Right. So just as I was saying with the question that Fuad asked, all right, one can say this animal began somewhere in this interval, at least the evidence began to grow strong within this interval. And these intervals differ dramatically depending upon the informativeness, the parameter that Peter Balsam was varying in that experiment. So now there's no quarrel about criteria, right? Because you've covered the waterfront with your criteria and you see that the effect is there independent of the criterion. So that's the effect of the informativeness. And in fact, I'm going to recommend to Justin I think he'll be pleased. I'm conceding that he's right, that they sometimes do require gradually, and that here's a way of characterizing it rather than curve fitting. Trying to fit curves to this kind of thing is a kind of a fool's errand. I did a lot of that back in the day, but I eventually concluded that that was because you don't really know the form, right, of the function. The only thing you can say with some confidence is that whatever the form of the function is, it rises from negligible to very substantial within this interval. All right.
There are at least two questions in the chat box. Rodrigo, would you like to voice your question or would you like me to read it? What's your preference?
Okay.
Yeah,
Well, my English is not too fluent, but I guess I could try. I'm asking whether could the retrospective association process work for recent patterns of responding instead of solely for a single response? I'm thinking in fixed interval responding.
Peak, you're thinking of the peak interval.
Yeah, in the whole pattern, rather than in the last response emitted.
So if I understand the question, I think that I have not actually used it with peak interval data. I believe that it should work very well. And I believe, again, consistent with what Fuad and I have been more or less agreeing on, that what you would probably want to do is run it from both ends. You would want to define the interval over which the subject was ceasing to respond. Does that answer your question?
Okay, maybe, but relatedly, I ask whether is there a way to include an inferred estimate of the cost of responding in this prospective and retrospective system, which I found very intriguing.
I'm not, Fuad, can you help me? I'm not sure.
Yeah, so I think the initial question had something to do with when you talked about prospective and retrospective associations.
Yes.
You took the last response in the case of right? You took the last response as the reference of how informative it is with respect to the average response rate. The question Rodrigo is asking is, I guess, rather than taking that last response as a reference, can we take a window over which there's a response rate and compare it to the background response rate type of thing? That's what I understood from his question. I don't know if that's right.
Is that right, Rodrigo? Is it?
Yeah, I'm thinking in accelerating or decelerating patterns in for example, in fixed interval typical performance. That's it. I'm not referring to the response rate as a whole, but in local patterns.
Yes. I've done a lot of sort of fooling around with local patterns. What I've mostly found is that it's hard to find consistency across subjects. I mean, the individual subjects certainly do. One of the ways I put this, and many other people I think have noticed the same thing, is the notion that there is an asymptotic response rate is a bit of a myth.
Right.
Because from day to day, the animal has off days. So he may be banging away very nicely on one day and then not responding very well on another day for God knows what reason, right? Bashak has also used the NDKL to decide whether in a choice experiment, the animal's choice rate has stabilized. And that worked really quite nicely. And again, it showed that you could have been much more efficient because, you know, as usual, she had adopted some criterion, and she's a very careful experimenter, so it was a very stringent criterion. Right, but when we ran the NDKL, we saw, oh, look, that animal had a stable choice rate about 0.9, if I recall, 0.91. Going back hundreds of trials, there was no evidence that the rate was changing. And you know, your experimental time is, there's a cost there. If you've got a way of saying, okay, we've got the stability that we want, let's go on to the next phase, you can finish your experiments much more quickly. In the peak procedure, as you know, there's going back to Church and Gibbon, there are attempts to say just how abruptly do they change, and the general answer is that it's pretty abrupt on an individual trial basis. And people have come at that in very different ways. The Church and Gibbon created a template. I've done, with Matt Mattel, I've done Bayesian approaches where you, and they generally agree in their conclusion that on most trials, there's quite an abrupt, particularly the cessation of responding. The onset of responding is much noisier in a peak procedure. But the cessation of responding tends, well, Fuss done a tremendous amount of this kind of thing. He can weigh in on whether my generalizations are true or not, but there seems to be pretty general agreement that the cessation is quite abrupt. The onset is messier. For one thing, you get impulsive responses at the beginning. So it's really a mixture distribution. And then we've wrestled with that in various ways.
Peter Coyle has a question. Peter, would you like to voice it?
No, I prefer not to at this time.
Okay.
Ask the question anyway.
Right. So is the change point of ITI when the derivative of the curve is 0 or only approaching 0? That was the question.
What was the question again?
Is the change point of ITI when the derivative of the curve is 0 or only approaching 0? I don't know if that question still holds. I wasn't sure from what Peter said, so that's what he wrote.
I think that one of the subjects, it looked like they sort of acquired immediately because they would start it off for a second. Obviously, you can't tell, right? When you're dealing with 1 or 2 data, small sample fluctuations raise their head big time, right? And it's kind of a fool's errand to try to argue, oh, this rat required that. Right. Now, next lecture, when we come to the pigeon auto-shaping experiments, there I think there's compelling evidence that when you set the informativeness to a very high value, around 300 or perhaps a bit higher, most birds learn after a single reward. The key light comes on, the reward is delivered, and the next time the key light comes on, they're already pecking the key light, right? And I think the evidence for that is quite strong. And that's partly because the spontaneous rate of pecking in these pigeons is so very low. So you get that kind of thing.
Well, I have a question.
Yeah.
I do have a question. I'm looking at the pokes per minute slide. And as I look at the red line and the black line, whenever either of them peaks, the other one inverts. So there's something going on with the derivative in those lines.
Yeah, no, sure.
At the inflection point,
So-
things change.
Oh, you mean like over here?
Yeah, well, follow it back up a little bit to the peak, over to the right.
Yeah. So keep in mind that over these first few data,
They don't.
it's, I mean, you've got big, small
There
samples.
they're crossing there.
So let's see. Here, you see on the first trial, it pecked very infrequently during the CS and very frequently during the ITI.
Mhm.
And then on the next trial, it's the estimate of its peck rate. I mean, keep in mind, these estimates, of course, are extremely noisy, as you can see. And you can see that they're stabilizing, which is what you expect. On the next trial, it went up to here. And this was here. And the NDKL went up a bit. Keep in mind, it's in the noise range. This is all noise, basically. Now, I don't think I can unpack sort of on a datum by datum, but I'm happy to send anyone who wants to look at the individual data. I'm more than happy to send them, and you can sort of study what's going on here. I think you're
Well, where the pointer is right now,
yeah.
you're getting inflection points on both curves, both
Yeah.
the red and the black. There's an inflection point on both of them. They're
Yeah,
changing direction.
yeah, that's true.
And then go over between 40 and 50 milliseconds.
Yeah, 40 seconds.
what-
Yeah.
Well, yeah, a little bit more,
this-
more up.
Okay, so 40 USs, yeah.
All right, move to the right a little bit more. I can't see your pointer. Right, what, a little bit more, where the two intersect, the red and the black intersect.
Right
They're
here.
both an inflection point, yeah.
So I mean, without going back and walking through the data datum by datum, I can't really explain what's going on, but bear in mind, the rates are jointly determined, of course, by the counts and by the durations. And the durations, so the count may stay the same and the durations for these two, for this and this, are not incrementing simultaneously. In fact, you're getting different increments in these durations than you are in these durations, right? Because these are incrementing from the intertrial intervals, which are exponentially distributed, and these are incrementing from the fixed duration. So, and all of that's interacting to determine the rates and then to determine the NDKL. So as I say, if you want to unpack what's going on here, the only solution is to look at the raw data.
Well, this doesn't seem to me like it's a random occurrence of those two curves, when their inflection points change.
Well,
Or when at the inflection point, the curve changes, and it just doesn't seem to me that that's a random thing.
But there are many other cases where
but
they don't coincide either. So
yeah, that's true. That's true. I suppose one should count and do a probability on that.
right.
It's also worth bearing in mind, and I think this might be a big part of what's puzzling you. Keep in mind, we're in negative territory here, right? So when this is going up, it's actually getting smaller. Okay, does that help? Here's 0.
Okay. Yeah. Yeah.
Okay.
Okay.
So here you see these two estimates coming
Getting larger.
and this is getting smaller, which is what it should be doing, right?
So in all cases,
the black-
actually, the evidence favors responding during ITI. in this
Oh,
case.
yeah. Oh, that. But keep in mind, this is telling you that you shouldn't take these differences seriously, right?
Right, exactly.
The evidence for this difference is very weak, very weak. It's
But if you find that change point based on the NDKL and look back, now what you don't find very reliable might become a little bit more informative now, because later on there's decisive evidence that responding during ITI is so I guess what I mean is what you find with a very liberal criterion early on is actually maybe becomes a bit more important.
that's my own feeling too. That's why I created these multiple criteria, and but we'll see how. It's at this point, it's not entirely clear to me how important this is or isn't. It was very important to Peter and me that we agree that we had an algorithm that would say where the animals acquired, and when we looked at the data in each animal, we would agree. We'd say, yeah, that's right. But we did end up using these multiple criteria for just the reasons I've explained, right? We wanted, in effect, we ended up saying, look, we believe this. We think this is where it really started, right?
Right.
But, you know, and again, I stress that when you get to bigger informativenesses, then this thing just is a cliff, right? But this becomes an issue mostly only when you're, this data, this is only an informativeness of 5. The pigeon autoshaving goes all the way up to informativenesses of 300, right? So, and that's where you get one trial acquisition, right? So, and also this subject is unusual. Normally in informativeness, you do not get one trial acquisition. So if you're a Bayesian, you would put a sort of group prior on it and say, well, you know, given the group that this was in, we shouldn't believe this and so on. Whereas when you get up to 300, the data look very different.
Randy, I will have to leave for a thesis proposal. I apologize for that, but the rest of the audience, please feel free to ask your questions. Ece will be here to moderate. Thank you.
Thank you. Thank you for what? No questions? There are no questions. We'll call it a morning or a day, given that we're spread all over the world. All right. Good to talk to all of you. Stop. Now I have to end show. There we go. Stop, share, leave.
Okay, if there's not any more questions, then we will close the meeting. Thank you all.